Today we're going to talk about an interpretation of the paper AI models collapse when training on recursively generated data. This paper talks about uh, the risk of using data generated from previous models instead of uh, use the data that is produced by humans. These practices have been growing since the people tend to train their model from information in the internet, and the internet is more and more information produced by previous models. So the work present the risk, as we were talking, especially for the large language models like the GPTs, that they can collapse by the indiscriminated use of the data that is generated from previous models. The amount of information published on the internet is going to keep growing, coming from models, and it's as it's they generate the process. The model have two types of collapse. One, you can see it at the beginning of the model, the early model collapse at the beginning of the new generations. Uh, it start to look information about the tail of the distribution, because basically the models are going to start eliminate words with a lower probability, and as the generations keep growing and growing, those words are eliminating, it keeps eliminating words. Its end not resemble the original one, and that's when it collapses. It's used on models. One is with this discrete mode, and one is basically in the Gaussian. The theoretical intuition. The model collapse is universal among generative models that recursively train on data generated by previous generation. As I said, two models has been used for this paper: a discrete distribution in the absence of functional expressibility and approximation errors, and one multidimensional Gaussian. Uh, the first model, which is the discrete distribution with exact approximation, considers a discrete probability distribution defined as the function of the probability, the one p. The model collapses only because of statistical error from the samples. First, the low probability events start to disappear as the probability of sample then is reduced. We shrink the distribution over time. What it means is as the model, the next model, the model reduce those samplings with low probability. It won't be available. Some of them is not going to be available for the next generation. And as it goes reducing, it basically just start to, and generations start to feed the same data. There is no much variation. And so basically we can see it as a demonstration from the authors that if we have x1 and it goes through the function, and it results in a probability which is going to define the next generation, and as a Markov change, all of the next generation is going to depend on the previous. If all the x have the same value at the next generation, the approximate distribution will be exactly at a delta function, and the previous generation is going to be the same at the next generation is going to be the same as the next, and it implies that the Markov change contains at least one absorbing state, which is basically very difficult to go out. They are another supplementary information in the paper with more calculations. In the case, this model and the next I want to look at it, uh, they fail either in the early stage or start to reduce the probabilities events in the early stage, and then collapse uh, at late stage. The next model that we're going to talk is the Model 2, multidimensional Gaussian. This assume original data is sample with non-zero sample variance. Uh, that sampling not necessarily is Gaussian. Assume that xn are fit recursively using unbiased sample means and variance estimator from previous generation with a fixed sample. Again, the next, as the error, the bias start to reduce uh, when it tends to infinite generations, then the deltas are going to be practically zero. From these, the end generation diverge arbitrarily far from the original, and as the number of generations increase, it will collapse to be zero variance. What we talk about when we say about model collapse in language model, this is a degenerative learning process in which the models start forgetting improbable events over time as the model became poisoned with its own projection of reality. The model collapse is universal across different models of machine learning. Since the large language models are so expensive, people tend to use pre-trained with BERT models like BERT, Robert, or the GPT, which are trained on original corporate data. Then they are fine-tuned depending on the task that the ones they use. The autos fine-tune the OPT 159 Castle language model, which is available by Meta through Hugging Face. It was turned on Wikitext datasets. The training sequence were blocked to 64 tokens, and each of those 64 tokens are going to generate the sequences to predict the next 64 tokens. The training for each generation start with the generation from the original training, and then each experiment was run 5 times. So basically, start the data is the original, but then every next generation is going to feed up with a different data. The two models, then we have a first setting. This is with the it was run for 5 epochs, no original data. What means is start with the original database, but then next generations were fed with no original data retained for subsequent runs. They found that the training with generated data allowed them to adapt to the underlying task, losing some performance around from 20 to 28 perplexity points. The second setting that they did is running 10 epochs instead of 5 and feeding is the next generation instead of being totally fed by previous generation. They will randomly take 10% of original data on those samples, which means is next generations are going to be fed with, or they were fed with 90% from the previous generation and 10% with original data. In this case, the preservation of the original data make the model run better, and it was only minor degradation of performance. The result, both training Raymond led to the great performance, and the model. Uh, they found out that they could actually get models, got good results, but the collapse will occur at the density of sample with low perplexity begins to accumulate over the generations. Of course, these were few generations that they did, but they demonstrate the effect or start to see that fall uh, for the model to collapse in more generations. Uh, how to discover that generated data have much longer tails, suggesting that some of the data will never be produced by the original model. These are errors that accumulate because of the learning with generational data. Uh, then the probability of the models tend to produce more sequence uh, than the original data and start introducing their own improbable sequence. That is the errors. There is an example that they show here, and we can see from the input that talk about some point in 1360. It's a star that some of the work started in 1360, accomplished by a master mason of a small team of itinerant mason. And basically, it's our architecture. Then the generation zero, it has as an output talking about the St. John Cathedral in London, and start to change the century and some errors in work. The first generation then talk about the St. Peter Basilica in Rome or St. Peter Basilica in Buenos Aires. It start to introduce more errors. The fifth generation is basically just talking about language, and the ninth generation is all error. Thank you very much.